Okay, so hello everyone. Again, we have a couple of minutes, so let me take questions if you have before we start.
I had a question about when we're starting Java.
Next lecture,
Okay.
hopefully, yeah. So this year we are covering a little bit more topics than what I did last year, and the reason for this is I believe those topics that we didn't cover in last year. So I'm replacing some of the topics in Java with some of the topics in C because especially the last lecture and this lecture, they are two important topics that I believe they are very useful for you, both when you apply for industry positions, whether this is like internship or even when you graduate, and also when you take other courses, right? So for example, embedded systems, computer organization, doing any project work that would require programming, recursion is an easy way of doing things, which what we discussed in last lecture, and what we are covering today, which is Bitwise Operations, especially very important for any kind of microelectronics work or circuit work, or even digital communication for those who are working on communications as well. Yeah, Elizabeth, I'm uploading this. I was just taking questions while see to upload them. Okay, that's topic 13. Question, Gottung. In question 3 of lab 3, can we assume the length of the word? If the question is generic, which I remember it is, you shouldn't, Gottung. You shouldn't be assuming the length. Yeah, for midterm, I didn't say anything yet. But I'm going to say, like, I guess I'm a bit unstable now, but hopefully I'm back. So yeah, if I'm back, please guys confirm that's the case. We should comment out this week. When will the mark be posted? Okay, all of this is coming. Is it still frozen? Okay, thank you. Thanks, everyone. Okay, so let me first upload the lecture for those who would like to look into the lecture in their terminal. And then I will continue. So someone was asking about the lab and again, I'm not expecting. So or you shouldn't be expecting the lab. So the lab is initially empty, so it has no implementation at all, right? So it shouldn't run. Generally, before it was running because like returning 0 was like a default, right? So you just like the test cases are calling your questions why they are empty because they take nothing back. But a short answer or a short solution, if you are trying to run the starter code out of the box before implementing anything, is just to comment out the test suite line of code when you include the test cases into the test suite for question 3. I guess there are only 2 tests right now for question 3. If you comment these couple of lines in the test cases.c, this should work completely fine, right? Again, if you have other questions, let me know while I'm uploading the lecture, and we then can start afterwards. Okay, so lecture is uploaded. Hopefully you will be able to access it. And I assume you are seeing my slides right now. So if there are no more questions, let me see the chat here. With the midterm, I am going to comment about this. So should come now with the suite test cases for question 3 until I start doing it. Yes, Vito, that's the case if you want to test other codes. Yeah, that's okay, good. Okay, so for those who are asking about some of the logistics, including the midterm grades, so just to few announcements here. You might almost all of you, I guess, received emails yesterday from Zoom to update, like as an update for the lab section meetings in Zoom. The reason for this is I wanted it back to go normal to what we have been doing before the reading week, which is we start by the even lab sections, and then the second week of the lab is for the odd ones. So you should have received these emails. If you didn't, I mean, you wouldn't, don't bother at all. Assume your lab, if you were attending the second week in a certain day, it would be exactly the same thing. You would use exactly the same link. So you shouldn't worry about anything. If you receive the emails and you don't want to bother, just do read them. They're just telling you that things are updated. For those of section 2 and 4, which previously was shown to be yesterday and on Monday, while sorry, this is supposed to, yeah, so while they were supposed to be yesterday and on Monday, while according to the old Zoom links that were recurrent because of the reading week, they which have shown in their calendar, if they added to the calendar, to be next week, just to accommodate for any confusion. For section 2 and 4, only for lab 3 you can also attend next week, which is for lab 1 and 3, Monday and Tuesday, right? Just to make sure if you missed this week lab, you wouldn't worry. You can come to the next week lab session. Again, lab session attending is not mandatory. I mean, by now, half of the semester, you already know that. I see from my attending in the lab sessions that really office hours are more busy than lab sessions. I guess the reason for this is the flexibility that office hours are offering for you rather than dedicated time for your lab session. That's completely okay. I'm open with this. It's one way to help during these times. So if you seek help during your lab session, perfect. If you seek help during office hours, that's also perfect. We have no issue with this, except that you shouldn't be attending any lab session other than yours, right? And the reason for this is lab session is the right for those sections registered for this lab to receive help with a small number. Usually we have less than 30 students. So attending to another lab session would interfere with the right of other colleagues, right? But other than this, feel free to drop in office hours. That's okay. Again, for those who never use the office hours, we have office hours daily from 10:30 to 2:30, and it's just the same link for every day. With regard to midterm grades, my original plan was to announce them today, in fact, yesterday night and then today morning, but I have to delay them until tomorrow due to some things I need to organize in some questions. But basically, overall, right now, when I looked into the grades, they really look fantastic. Like the average is 80%, which is really high. I know that the exam was a bit easy, but you guys did great as well, so that's perfect. I mean, with the uncertainty in the environment, also this is something that is good. So yeah, well done everyone, and hopefully by announcing the grades tomorrow, if you got any questions specific to why I did that grade or got that grade, just send me an email or Salah, like the master TA. I will announce this maybe by Friday, but the point is you have a time to see your specific grading. Why did you lose things? We can look into the code together, and hopefully you might get more marks or lose marks. This depends on me looking into the code, because I'm not the one who did the grading for all the questions. But you would take the risk if you want. Let's first look into the grades, and then we can arrange this time together, how to see really why did you lose marks, or why you did get a specific mark in a specific question. I have received some emails from you yesterday and on Monday. I would apologize for not following my convention to respond maybe within a day or so. but I will get back to everyone emailed me during this week by tomorrow. So hopefully you would bear with me after I finish this midterm grading. Okay, so everything is good. No more questions about anything related to logistics or anything that we need to discuss before we start. So I would start and then I will keep looking into the chat as usual. So Bitwise operations, what are Bitwise operations? Hopefully by now, I would assume you guys, at least most of you, know binary representation, hex representation from the digital design course. Some basics about the gates. I guess also to some extent this is covered in high school right now. So hopefully you have like the necessary information. It's minimal information, but it would be very hard to go through this. And it's not the focus of the lecture. The focus of the lecture is how to do this in programming in C, right? So some knowledge of gates or binary like representation of numbers is really needed here, right? Yeah, I know that some didn't take that class, but again, the information that is needed is only like the basic information that every decimal number can have, like a binary representation number. And I'm assuming this is covered in high school. If I would also go through this very quickly, you don't need to know much, but let's see. If you got questions, ask as well. Okay, so operations. So let's first of all, when we define types in C, one of the aspects of any type. Types like int, float, double, whatever, we said there are three aspects of a type. One of them is what are the operations that can be done on that certain type, right? Bitwise operations are only done in integer types. Integer types including int, short, long, signed, unsigned, and character. Why character? Because remember we said character is really represented in C as 1 byte integer at the end, right? Due to the ASCII representation, every character has its own number representation, so it's int at the end. Correct? And we have run like some examples of how to print A in int and A in character. And we have went through all of this. Good. So what is bitwise operation? So simply every number, every like integer number can be represented as a binary representation. And then we can manipulate those bits. Oh, I went also glitch again. Should be back. Okay, so let me repeat like the last 30 seconds. So again, like every integer number can be represented as a binary representation. And this binary representation, like you have certain stream of bits or representation of bits, and then you manipulate these bits. You do some operations on them. You compare them, you shift them. You will see right now you AND or XOR them using some logic gates, right? And the main topic of this lecture is how to do this in programming, right? And we will see why it's important. Some of the applications of bitwise operations is digital communication hardware design. For example, assume you want to design an adder circuit, right? Or a shift left circuit or something like this. So what is an adder circuit? In your laptop, you have what we call ALU or arithmetic logic unit, where simply if you run your C program adding two numbers, you need some piece of hardware that does the addition for you, right? At the end of the day, there has to be an adder there to perform the adding operation, right? Nothing is done really in software. Software is just a representation way. All the algorithms at the end go to the hardware to execute them, right? You need to kind of understand this interaction between software and hardware. And our lecture 0 was mainly about this, how really what we do is very, very high level in C programming. I mean, not very high level. We see Java is even higher, but basically in high level programming languages, and then you go to instruction set architecture, logic design, computer architecture, and at the end you have some piece of circuit which is inside your processor where performs the addition, subtraction, multiplication, and all other operations. Good. So in hardware design, you need to do these kind of operations on bits. And in digital communication, similar thing. Assume, for example, you receive a call. How would your phone know that who is the number that is calling you, whether this is your friend or your mom or your dad? The way this happens is you receive a caller ID from the BTS, like the base station of your mobile network, and it receives the caller, like it sends the caller ID represented as some code, which is in binary, and it's also encoded for security reasons. Your mobile receives this, looks into the bits. Now, as a user, you wouldn't be expecting when you receive a call, instead of like showing dad, you chose like 10111, right? This makes no sense. So you need some way of translating these encoded bits that are transmitted into the air to something meaningful. So you need to decode these messages, and for decoding, you need to manipulate the bits to really have some meaningful representation for you as a human, right? So in digital communication, because we transfer everything as bits, we need to manipulate on bits. Another advantage of Bitwise Operations is really some of the tricks that are done in hardware design, especially for embedded systems. For example, in like avionics, automotive, IoT devices, like wearables, smartwatches, is you want your hardware to be efficient and faster and consume less energy, right? The way this would happen is you, for example, if you want to do a multiplication is a very expensive operation. For those who are taking digital design later, they will see that. So how I can do multiplication without really multiplying on this big circuit? You can just shift a number to the left. We will see right now what we mean by this. But if you understand binary representation, shifting a number, just a simple shift, gives you the multiplication operation. Or on the other hand, if you want to divide, shift to the right, you are dividing by 2. So, and why 2 is something that is important. I mean, if I'm just dividing or multiplying by 2, it might seem just a single number. So it makes no sense because you need to multiply to other numbers. The hint here is because most things are in the binary format, they are in the power of 2. If you think of your hard drive, for example, you say like terabytes, like it's 1 terabyte, 512 like gigabytes. Look into the numbers, they are always in the power of 2. Again, your DRAM, your memory chip is like 1 gig of bytes, 2 gigs, 4 gigs. It's always also in a power of 2, right? So everything almost in digital technology we have, whether this is digital hardware or digital communication, is dealing with numbers that are power of 2. So being able to divide or multiply by power of 2 is really something powerful and is needed most of the time. You really multiply by another number, right? In these kind of fields. So being able to multiply or divide by power of 2 in a cheap way through shifts, for example, rather than multiplication and division, is an advantage, right? I don't want this lecture to turn out to be a hardware lecture, but just to give you the context of why we are doing what we do. And this is one of the lectures, again, that software and hardware really interacts together. So binary representation of unsigned integers. So for those who didn't take the course, didn't touch this in their high school, let's have some brief background. It's going to be very brief, but hopefully you'll be able to catch this. So assume I have some unsigned integer x, right? It has like a value of 130, 150, whatever the value is. Excuse me. If you have 1 byte of this, 1 byte is 8 bits, correct? So I have these, let me use my pen. So these are the 8 bits of the number from 0 to 7. And the way you can get the binary representation is like, or transform from decimal to binary or binary to decimal, is you know that the first bit is 2 to the power 0, the second one is 2 to the power 1, and then the more you move to the left or to the most significant bits, the power of the 2 increases, right? So if we have one example, if this is a binary representation of a certain number, how to obtain the equivalent decimal value, which is 51 here, I would take the first bit, 1, multiply it by 2 to the power 0, and then the second one 2 to the power 1, 2 to the power 2, the last thing is 2 to the power 7, add all of this together, and this gives me the decimal representation, right? So the general equation here is you take every bit, you have I bits, so for all I, you multiply by 2 to the power I, and then this is multiplied by the bit itself, bit I. For example, here, the first one is 1, so this would be a 1, and you multiply by 2 to the power 0 because this is the first position, so to the power 0, which is the first term here, second term, third term, etc. Is that clear? If you have questions, please ask. So is there a problem with, let me, I guess this was a while back, but should be stable now. Okay, good, thanks. So hopefully those that were worried about the background, now they know what is a binary representation. If you got questions, please ask. And then it remains to know, okay, now we discussed general binary representation. We want to match this to our C programming. So we said unsigned numbers are three things that bitwise operations can be done on. We have characters and short and int, right? A character is 1 byte, so it's just the 8 bits we have of the number. What about short? Short is, as we discussed before, 16 bits, which means 2 bytes. If the number is representable in only 8 bits, the remaining most significant 8 bits would be just 0, right? So when you declare a variable as unsigned short, 16 bits get allocated to you, even if your number is not using all of them. The remaining ones would be 0. This also gives you a hint why what I said before as a good programming practice to use only the memory storage or the variable type that you really need. If you know, for example, all your numbers are less than, here we have 8 bits, 2 to the power 8 minus 1, 128. Then you would be better doing it as character, because you would be wasting extra 8 bits or 1 byte, or even in the case of the int, which is 32 bits, you would be wasting 3 bytes, right? So if your number is small, but on the other hand, if you know that your number can be a little bit large, then you would need character, would cause you an overflow, which means it's not going to be able to represent, for example, 300. Then you need a bigger representation. So the trade-off between larger range of numbers or larger sets of numbers to represent and wasting memory is what you need to know here. You need to ask yourself, what is the range of my variables and how to implement them. Those who are, again, doing some projects later on in any digital design or microprocessors would be in kind of incurring or encountering such trade-offs. Okay, for signed numbers, I would just leave this for now. It's kind of optional. Let's go back to the main thing that we're discussing, which is bitwise operations. What are bitwise operations? They come from the logic gates. So we have an AND bitwise operation, XOR, OR, and then complement or not, right? The main thing that is important to know compared to for example, like the conditional operators, because in if conditions, for example, remember we were also doing this AND thing. Like we'd say, for example, if A is true and B is true, right? So now we have two different things which might be confusing. We have bitwise operations and we have logic or conditional operators, right? So what is the difference between them? Bitwise operations, from the name, by definition, they are dealing with the bits at the bit level. All variables are dealt with like bit by bit, right? We will see an example right now. So for example, if you know that A and B, their bit values are 0 and 1, A and B, it's similar to the gates again. If A and B are correct, like or true, then you would get 1, you would get 0 otherwise. Yeah, complement AN is the not operation, right? So it's like if 1, then not 1 is like not true is false and not false is true. You just flip or negate. Sometimes it's called negation, complement, not. But complement is the terminology used in digital gates, right? And then this is A or B. So again, the same meaning of OR. They will be 0 only if A and B are zeros. This is XOR. So if they are different, gives you 1. If they are equal, it gives you 0. And then this is the negation or the not operation. So it's 1, it gives you 0. So this is the table for the bitwise operators, similar to, again, the gates. If you have X and Y, all the values of X and Y are here. You have 4 different values. If X is 0 and Y is 0, then first of all, the AND gives you 1 only if both are 1. The OR is the other way around. It gives you 0 if only both are zeros. XOR gives you 1 if they are different and 0 otherwise. And not X, simply just flipping all the bits of the X. Good. So again, this is some background in logic. I will explain now the difference between the not, like the difference between this and this, right? These two are different. So as I was explaining and like just a single AND, this is the logical or conditional operator. This is the bitwise operator. We will come into the comparison between both right now. Okay, so let's have an example. after all of this theory. So I have x with like a random decimal value like 65 and y is 90. If I want to get the representation of x as an int, then this would be the 65 value for an integer. How we would know this, just again like touch in the background, this is 2 to the power 0, so it gives you 1 plus 0, 1, 2, 3, 4, 5, 6. This is 2 to the power 6. 2 to the power 6 is 64. So 64 plus 1 is really 65, right? And then y is to get the bits, it gives you that, right? So let's do some kind of bitwise operations on these two numbers. If I'm doing x and y, what is the difference between x and y and x and y, like the conditional or the logic operator and the bitwise operator? Let's do the bitwise first. The bitwise operates in a bit level. So it takes bit by bit for everyone, every corresponding bit. So bit 0 is bit 0, bit 1 is bit 1, bit 2 is bit 2, etc. And it does the operation. So 1 and 0 is 0. You will see that it always gives you 0 except for the two bits that are 1 and 1, right? So this is the value that x and y gives you, right? On the other hand, if I do, just for sake of comparison, if I do x and y and y, can someone imagine what would be the value that I get as an output? This is something that we have been doing before. 1, exactly. And how to write this one? So 1 is a decimal value, simply the binary representation of a 1, sorry. The binary representation of a 1 is just 1 and everything else is 0, right? So you see the difference here. This is done by bit by bit operation, while x and y is taking x as a whole number. It doesn't look into the bits, right? Good. So this is x and y. What about x or y? If I do an or, I would be giving 1, except that where all the bits are zeros, right? So for example, 0 and 1 is 1, 1 and 0 is 1. Here 0, 0 is 0, and everything afterwards is 0, so it just gives you zeros, right? So the or is doing the or at the bit level, the and is doing the and at the bit level. And then x XOR y, it gives you only 1 if they are different and 0 otherwise. And then finally, not y or negating y is just flipping all the bits, right? As you can see here, all these zeros are flipped into ones and zeros are flipped into ones, ones are flipped into zeros. Again, let me say, if we do not y to explain the difference between logical and bitwise operations, what would be not y giving you? 0, right? So, and 0, if we look into their binary representation, everything would be 0, right? So it would be just giving like a stream of 32 zeros, right? So this is the difference between bitwise and logical operation. Is there any question? Because this is the fundamental, I would say, knowledge. If you get that, we're almost done. We will only see some applications, right? But this is the basic knowledge. So if you got any question here, let's stop and take questions to make sure if when we go to the example, you guys need the basics. Okay, good. So no questions. Will we do bit shifts? Yeah, I will comment on example of shifts. That's, yeah, we will do it, guys. So again, like elaborating a little bit more on the comparison between the bitwise and the logical operators. Let's take the bitwise OR compared to the logical OR. X or Y is giving you 0 if both X and Y are zeros. It's all zeros, and it's false if both are false. And the point that this is making here is, if you are looking either for a false or true output, for example, inside an if condition, it's safe really to use the bitwise operator instead of the logical one, right? There are some differences, that some tricks we will see right now, but generally, because the OR is also giving you, the bitwise OR is only giving you 0 if all the bits are 0, so 0 and 0 is 0. At the end, it gives you false. So it can replace the logical operator from the function of the logical operator. On the other hand, logical cannot replace the bitwise one, because the logical operates at the variable level rather than the bit level, right? What is the difference then if the bitwise OR can replace the logical OR? Remember, we said in one of the lectures, review lectures before the midterm, is that doing the OR, the compiler is trying to do an optimization where if it finds, for example, if I'm doing X or Y, and or here is the logical one, and like or like two ones. If I'm doing this and X is true, so true or anything is really true, so the compiler will just ignore the second one. Remember, we have discussed this before the midterm, right? So if I'm doing this here, and I know that X is true, the compiler wouldn't compute this this expression, and hence Y will not be incremented, right? So if Y initially was 0, afterwards Y still be 0 because the increment didn't happen, because this expression didn't happen. On the other hand, the compiler has to really calculate both expressions in the bitwise OR, because you have to take them bit by bit. So you cannot just say, if X is true, what about the remaining one? Because it has to go to the bit level, so always the increment will happen. So the general rule is, in the logical OR, if the first expression is true, the second one is ignored. While in the bitwise OR, nothing is ignored. Always all the expressions will get evaluated. When this makes a difference, this will make a difference when you have a pre-increment or post-increment, because this only happen after the expression or before the expression is calculated, right? If you get questions here, please ask. You can, Zawhan, if you are asking how to print f X or Y, these are normal ints or characters, so you can just print them exactly the same way. If you are asking how to print them in a binary format, then you would have, we will see right now how to do this, but there is no straightforward way in C to do that, right? Yeah, it's still int. The result is still int, right? The result is exactly the same type as that both inputs. Okay, just no. Okay, no more questions. Good. Okay, and is the same, exactly the same way as the logical and, so both can be replaced. And like when I say both can be replaced, like the bitwise and can replace the logical and, not the other way around. And the reason for this is, again, it only evaluates true if both are true, right? But you would also ignore the second expression if the first one is false in the AND case, while for the bitwise AND, you don't ignore anything. Any question before? So this trick of ignoring, not ignoring based on the bitwise or the logical one is an important one. So if you get questions, please ask before we move forward. Yeah, you cannot print in a binary way in C directly. You have to write your own transformation and or do some tricks that we will discuss right now. In C++ you can, but in C there is no direct way. Okay, so bitwise shift operators. So shifting is simply just moving bits either for left or right, right? So if I have one example, let's say X has this value, like again, the 65 value that we have from before. Let's focus on this X. So it starts from 5 zeros and then 1 for 65. If I'm shifting to the left, so I'm moving the bits in this direction. So that means the first bit now is empty. The way you would do the shift is you would place a 0 on the first bit and everything gets shifted by 1 digit. This is shifting by 1. If you are shifting by 2, you would be placing 2 zeros instead. How this, we said shifting to the left is equivalent to a multiplication. Why that's the case? Because if you take this value, you find it's 1 plus 64 as we have done, so it gives you 65. But now the 1 position has changed, right? From the 0 position to the 1 position. So now looking into this is 2 now, not 1, because 2 to the power 1 multiplied by 1 plus, this is now no longer 2 to the power 6. This is at position 7. So it's 2 to the power 7, which is 128. So this gives you 130, right? This 130, if you look into it, it's really 65 multiplied by 2. Since every position is 2 to the power something, once you shift every one by 1 position, you really multiply by 2. If you shift by 2 positions, you multiply by 4, etc., right? So shifting to the left, simply just placing zeros at the least significant bits. Least significant bits are the ones towards the right, like they have the least value, right, to the power 0 to the power 1. And then on the other hand, this is called shift left, right? Shift On the other hand, if I'm doing a right shift, so I want to move bits in this direction. So if I'm taking Y, this was the original value of Y. If I'm shifting it, I'm placing zeros on the most significant bits. So this now 0 will come out, and then the number will start from here. If you are shifting by 2, the 1 also will come out and will get out of here. If we calculate this, let's calculate this value. This is 2, 4, 6, and then 16. So it's 20. Let me just make sure. So it's 16 plus this is 6. So this is 22, right? Originally, Y was 90, right? Is this 22? So it's 2, and then 4 is 6, and then, yeah, this should be 22. So originally, Y was 90. So dividing 90 by 2 gives you 45, and then 45 by 2 gives you 22.5, but because this is an integer division, it ignores this and gives you 22. So shifting to the right is equivalent to a division. Shifting to the left is equivalent to a multiplication. Any question? Karina, so the increment still happens because it was bitwise operator. Is that always? Yes, Karina, that's always the rule. In bitwise operator, you have to calculate all the expressions. The rationale behind this, just to understand why it's natural, is you need the bits. You cannot just say this is true, everything else is false. It doesn't work like that. You have to take the bit level, and for that reason, you have to calculate both directions. So it's always the rule. Okay, no more. The monium, when it's bitwise, both sides of the OR are even. Okay, you were answering. Okay, good. So these are some other examples of shift left and shift right, and gives you the value like what I was doing right now. If 61 and then you shift to the left, you really multiply by 2. If you calculate the bits, it gives you something in the other. So here, if your value was 1001, you shift by this, you multiply by 2. If you shift to the right, you divide by 2, but you really do an integer division, so you just ignore the fraction. So this is now, it should be simple to you because almost any operand can be done with operand assignment as well. So saying x and equal y is simply saying do x and y and then assign the value to x. So you do the assignment and the operator on the same using the same operand, right? So that's just something that is similar to, for example, x plus equal y, right? You can deal with bitwise as normal operands here right now. So with precedence constraints, the bitwise ones comes directly before the logical ones, right? Some example, okay, that's good. So let's have an example to see how these things can be done. Like what is the meaning behind this? How we can use them in a program and how they operate, right? So in this example here, I'm not going to explain it directly. What I'm going to do is I'm going to run it and we discuss together how it works, okay? Let me just open the compiler and share it with you. Okay, I would guess you should be able to see, right? So this a little bit bigger. Okay, good. So I have a main here. So let's quickly go through it and then look into the output, try to understand what is going on. So I have, let me just remove this for now. So I have a program here, like a simple main. I'm just defining a normal character of 1 byte, has the value of 130. And then I'm here defining, what is this? Can someone tell me what is that? What is character asterisk S? Yes, it's a pointer, but to a pointer of type character, which is usually used as a string. That's correct. Thanks. So I'm defining here a pointer of a character which can be used as a string, and then I am reading the value out of a certain function. So now I jump to call a function, execute it, and then come back. And then afterwards, I print S, right? Which means simply what I'm printing is what this function returns, right? So let's see what does this function return now. It takes unsigned character as an input, which here I'm passing A to it. So the 130 will be sent to this function. And let's take it line by line. First of all, what does the first line represent? I'm using dynamic memory allocation by clock. What does it define in the memory? It defines 9 locations. Each one of them is of type character, right? So this is an array of characters of 9 locations. Each one of them is just a character, right? And then places this in a character pointer that I call buff or anything. Afterwards, I'm defining just my iterator I, and then I'm defining a mask. This can be named anything. It's just a normal unsigned variable, but I'm calling it a mask because usually most of the operations done in binary in binary format are called bit masking, and we'll see what we mean by this right now. Let's first take this line. I'm saying a mask has a value of 1, but this is shift left in this direction by 7, right? So initially, if it's 1, it would be something like this, right? And then a stream of bits, right? Correct? And then after I'm doing the shift, I'm shifting by 7, right? So which means I place 7 zeros, 4, 5, 6, 7 at the right, and then the 1 will become here right now. So shift left by 7 means the one that is at the beginning will go to position now. It should be 2 to the power 7, or the 8th position, right? So this is what does this line mean, right? Good. So now mask has this binary value, right? And then I'm doing a for loop that simply does some operation that I said I'm not going to explain until we look into the output. And then based on this for loop, I am assigning the buff array that I defined certain value related to X and mask, right? So let's run it and let's see what's going on. So if I just run this, I get this value, right? Let's see what is the value. So can someone explain to me what, or just directly get this value? What is the decimal representation of this value? So yeah, I'm just looking for the decimal value, right? So let's do it together. So this is 2 to the power 1, so it's 2, and then 0, 1, 2, 3, 4, 5, 6, 7. 2 to the power 7 is 128. 128 plus 2 is 130, right? So the value of this one is 130. If you look here, the input really was 130, right? Which means it's really the value of A in, how many zeros we have? 5. It's value of A in binary, right? So simply what this function is doing is transforming A into its binary representation, right? So it's a simple way of transforming this into binary representation. Is that clear? How do we do that? Let's see how do we do that. We really use the AND bitwise operation. Let's see how it operates, right? But do you get what does it mean, right? Okay, 130, good. So to understand how the program operates, let me go back to the slides. Then here. So we said this is the value of the mask right now, and this is X. Right now, I don't know the binary of X, so I'm just putting it generic, X0 to X7, because simply the input can be anything. If I'm doing AND, which I'm doing in the last line here, so this line in red, what it does, it's doing X bitwise AND with the mask, right? So doing this, what does it give you? You take every bit and it with the mask. So anything and with 0 is going to give you 0. And X7 and 1 is going to give you X7, because ANDing 1 with anything gives you this thing. ANDing 1 with 0 gives you 0. ANDing 1 with 1 gives you 1, right? So a trick in bit manipulation is if you AND with a 1, you still have the bit itself. If you AND with a 0, you always have 0, right? So it's like you are extracting the 7th bit of X, right? Good. And then the remaining of the line is saying if the value is true, you assign 1 into the corresponding position in the buff. So this buff is the array that has 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then here, starting from the position 7, for example, here I'm starting from 0, but simply I'm ending, let me see. Yeah, so what I'm doing is I'm ending, because I'm looking at it from the most significant bit. So in the first one, I'm ending X with mask, which give me 1 as a 8th position. So this is true. Then I'm placing 1 here, right? And then let's continue. Afterwards, I shift X to the left by 1, which means if X was originally that, shifting it to the left by 1, placing a 0 here and losing the last bit. So now this is the new X after shift lifting by 1. And I'm repeating the masking operation, which means I'm getting X6, right? The 6th bit of X, like the bit in the 7th position, and then X5, and then X4, and then X3, right? So each time I'm extracting a certain bit and seeing if it gives you 0, you put it here. If it gives you 1, you put it here. So you try to check at each bit position whether X was originally 1 or 0, right? At the end, when we looked into the output, the final output of this string was really the binary representation of X. Because by masking, each time you extract a certain bit position, you check whether it's 1 or 0. If it's 1, you place 1. If it's 0, you place 0. Good? Is there a question? Yeah, Katie, it does. That's a good question. So here, for example, it does iterate through all the bits. So you take every corresponding bit, but the masking is the trick, right? The masking only has 1 at the most significant. So you always have 0 except for the last bit. At the beginning, the last bit is X7, but after you shift X to the left, the last bit will become 6. The third iteration, the last bit will be 5, 4, 3, 2, until you go through all the bits of X, right? Another way of visualizing this is you have a certain mask that is fixed. It has 1 here and 0s otherwise. And each time you do a sliding window of X, right? You start by X here, and then you shift X. So X now becomes here. This is bit 7 of X, X7. This is X6. And then you move it by 2 positions. So you have that, and this is X5, right? So you slide X such that each time you extract a certain bit. Yeah, because that's a good, okay, Kate, good. So let's go back to this line of code. Now I see your concern. So what you are saying is how this value is giving you 1 if, for example, there is a 1 and everything gets a 0. So let's take one example, right? Assume that X7 was 1, correct? That means 1 and 1 is going to give you 1 and stream of zeros. At the end, what is the value of this? Is it true or false? From our previous rule, we know that any non-zero value in X is true, right? So that means this gives you true. What if X6, for example, was 0, and I'm doing this AND operation, then everything here is 0, which means it gives you false. So if you look into this line of code, sorry, this one, this line of code is really this condition is true if the bit under examination or the last bit of X is 1 and is false if the bit is 0, right? Because all other bits are zeros right now. So the value of this condition, whether it's true or false, depends only on the last bit, right? And that's why it's called masking, because you mask everything except a certain bit, which you are investigating. I hope this answers your question. Thank you. Okay, thanks. So it just converts itself when you use bitwise operation. So it just convert. Yeah, Nicole, that's correct. Like the computer operates on really the binary values, right? But here, this program is just printing them for user readability, right? Good. So now we know that kind of the role of this program is simply to represent or print the binary value of a decimal number. Good. Can you explain again the mask initialization line? Sure. So this line, or maybe I just jump into the compiler to have it better readable. So here, so this number I really can replace with, sorry, I can really replace with two other numbers. I would say unsigned mask equal 1. Now this is very simple, but let's call it mask 1 for now, right? Equal 1. This is just a very simple defining an unsigned number, assigning it an initial value of 1, correct? Straightforward. And then afterwards, I can say mask 1 equal mask 1. I want to shift it left by 7 bits. 7. And then what does it do is it takes the value of mask and shift it left by 7, right? Which means if originally mask 1 was 1, which is this is the 1 value, shifting it to the left by 7, it gives you 1 at this, like the 2 to the power 7 location, correct? So you place 7 zeros at the beginning. Why I'm doing this? You're doing this because you take an input as a character input, which has 8 bits, right? That means you want to take your 1 to be only on the last bit. Going back to the slides, here, I want my mask always to extract the last bit, right? For me here, right? So I want the 1 to be in the last bit and keep moving X, right? If you think of that, you can really do it the other way around. You can keep your mask 1 and shift X to the right instead, right? But in this time, you have to start your array like the buff one from the most significant, not from the least significant. Arjun, instead of shifting X to analyze the leftmost, yeah, I guess this is exactly what I was saying, Arjun, yeah. Sagnan, why can bitwise operators replace logical operators when bit operators are not evaluated in short circuits? Yeah, so okay, good. They can replace it because they give you the correct result. Like whether any expression that is true under logical operands will still be true under bitwise operations. Any expression that is false under bitwise, under logical operators will still be true under bitwise operators, right? But as I said, they have differences of if you have a pre-increment or post-increment, you have to be careful, right? Nicole, why would you ever use Bitwise? Can you test hardware or something? Yeah, as we started like the lecture was, it has many applications in digital hardware design and in communications. For example, you do encoding, decoding. You want to extract certain bits, right? So I would say if, I guess we're already over time, but if you want more examples, I can share with you. I guess Arjun is already here. We have been doing a project during the summer to deal with memory like DRAM bits, right? In DRAM, you have banks, channels, ranks, and you need to operate in a certain segment. You need to do some bit extraction, right? So Arjun is kind of an expert right now in this. So if you want more practical examples, really my background is hardware, so I know how really to do this. We can discuss during office hours. I just don't want to transform the lecture to be a pure hardware lecture. But I would say Bitwise Operations is really one of the very useful programming skills when it comes to hardware and digital communication. Nicholas, so if we're doing this practically, would you have to write a function to find a binary length of X? No, you already know this from the type of X, Nicholas, right? We know a character is 8 bits, an int is 32, unsigned is 16, etc., right? So you know the length of the bits, right? From the type. Vector, why do we? So by the way, let me just conclude and then take questions. So the last thing before you all go is we have this additional example here that is doing some other example of bitwise manipulation, but I'm not going to explain it. I will leave it for you as an exercise to figure out what does it do, right? And then we can discuss at the beginning of coming lecture before we start Java to ask you what you have done. I take it as an exercise for practicing the knowledge you gained in this lecture. By this we are done. I will just keep for a few minutes to take questions, and you guys are free to leave. Yes, we are starting Java next lecture. That's correct. Okay, Victor, why do we make the size of buff 9? That's an excellent question, Vector. So we know that character is 8 bits, correct? But you represent buff to be a string. Remember, in string, you need one extra location to add your null character towards the end. That's the reason why it's 9, right? Because if you look here in this line, you have to put the last location of your buff as the null character. This is why it's 9. Yes, Nicole, we start Java next lecture. Jan, how are you going to upload today? I already uploaded the slides. Hopefully the video I should be able to upload as well. Are you going to, well, the yesterday lecture, yes, as well. Okay, are you going to be, okay, that's the same question. Would the final be about both Java and C? Yes, Ala, that's correct. The final would be, but because we had a midterm in C, usually the way I would do the final, but I will give you details later as I usually do. The thing is, usually the final is 1/3 C and 2/3 Java, right? That's usually the case. Because to accommodate, it's almost with the midterm and the final, we have 20%, 40%. I'm trying to make them 30% Java, 30% overall, like midterm and final. Together are 60%. So half of them are C and half is Java. So the final has to be also including C. More details will come later, but just to answer your question. Salah, what does this one do? It's simply shifting left X by one position and placing the result in X, right? Similar to what we do for, let me see here. So this is saying X equal X shifted left by one, right? If you go back in the slides, we have said you can really do this similar to saying X plus Y1. This is completely equivalent to X equal X plus one. The same thing, doing this would be equivalent to say X equal X shifted to the left by one, right? It's usually called assignment and operation expression. You combine both together just for simplicity. If you are confused, you can just simply write it in the long format. Okay. Is there any question? Yes, Salah, it's a decimal number, but any decimal number has a binary representation. I mean, all what we discuss right now can be decimal or character, and we said all the bitwise operations deal with integer values, right? Will you be showing us how to use Eclipse for Java in the next lecture? I would try to this in the tutorial. Usually we don't do things related to the lab during the lecture or the lab environment, but I might be able to do this through the Friday's tutorial, right? But really we don't need this until lab 4, which is starting the week afterwards. So it may be not this tutorial, the tutorial of the next week, right? Simply, if you have Eclipse, it works with Java out of the box. This is the short answer, right? Because Eclipse is originally a Java IDE, not a C IDE, right? You need some additional tools for C, but Java, it operates out of the box, right? But anyway, we can discuss this like during not the coming tutorial, the tutorial afterwards. Thanks, Arjun. Okay, thanks everyone. I guess I would talk to you on Friday then. Hopefully you would hear about the midterm grades by tomorrow, and these lectures will also be uploaded by tomorrow. Have a great day, everyone. Bye-bye.
1 second.